Okay, I was running into discrepancies that in the MATLAB version on Skybox and the one on my Mac computer, which I wrote the lab on. So compare with the document, the lab document. Um, this is an adjustment I'm making. So if we go back to so it turns out the Heaviside function used in defined in the Skybox version of MATLAB cannot be directly plotted because it's defined as a different type. What I did is add this double, so I'll convert the symbolic type of data to the double precision type of data. In this case, we'll be able to plot it without an issue. So we can see this function starts -10. This is how we define the time axis. And at time 0 jumps from 0 to 1 and remains 1 afterwards. Okay. So this is the step function. Now, the Dirac function, I believe, will be something similar. Let's have a look at it. So let me go back to here. Let me save it to 3. Okay. In this case, we can define y as a Dirac function t. Okay. So time axis still -10 to 10. I'm defining my Dirac function. So if I run this as a new file now, and let's see what happens. Now we have this y, and we have this figure. Well, it seems to be just a flat line, but if I zoom in using this, you can see there's a break at time 0. This is where the spike takes place, but on the graph, because it's an undefined value, cannot plot it, so that's why we see this break on the line. But I just want to say that this is how MATLAB can handle it. And you can also use your exponential signals, right? So this is how we define it. Let me copy them again. And I'll paste them to MATLAB code, MATLAB program. I'll replace these, paste, and I'll save as example number 4. Save it, and run it as usual. So I'll run using the green triangle. And there it is. So I have two exponential signals. One of the first y1 will be exploding to infinity, the other will should be decaying to 0. Now I'm plotting both of them in one plot. So the x-axis, the first function, the x-axis, the second function. And then the legend can include both terms, so you know which one is which. And the figure will look like this. Okay. So we have two, the blue curve and the red curve. The blue curve is the one that you plot first, and the first in the legend corresponds to this particular curve. In this case, will be the exploding one, and the second, the red one, is the decaying one. So this is example number 4, and it also shows on the screen too. If your exponent is a complex number, we can do something similar, but now because of the Euler's formula, we know it has two parts, the real part and the imaginary part, which can be done using the real and imaginary commands. So let me copy both of them again. Go back to this. I'll replace this part of the code. Paste. And I'll save this file to number 5. And you can see using the script will be easier for you to manage the code as well. Now you see here you have this I, which is also reserved to represent the square root of -1. It's the unit imaginary number. Now I have my time axis, I have my complex variable, and I'll take the real part of this complex variable and imaginary part of the complex variable. And we know it's going to be a cosine function, the other is going to be a sine function. And let's see. I run it. This is the figure. Now, from our knowledge, when we look at this exponential signal, because of the negative real part, -2, we know it's going to be decaying, and this tan basically means it's going to be oscillating, and that's exactly what we can see. You have two oscillating signals, this blue and the red. Okay? They have a phase difference because one is the cosine, the other is the sine. And also both of them are decaying as far as the input is concerned. This is due to this -2 in front of it. And you can use a MATLAB, you can visualize, you can look at what the signal is. Now, I believe with this few examples, you should be at least familiar with how to define a signal, how to plot it in MATLAB. Then what I'm trying to do next is to see, well, we have some manipulations as far as signal is concerned. For instance, you have this switch turn on and turn off based on the unit step signal, right? This is what we have. So if you have a signal, a sinusoidal signal, if you want to clip that signal, for instance, this one means a unit step of t minus 2 and another unit step of t minus 6. This is with our time axis. And this will form a switch that will turn on at time 2, turn off at time 6. And if you multiply this window clipper with the signal, the only part remain will be this signal from 2 to 6. But remember, when you apply that multiplication, because they're both of them are regarded as vectors, and what you're trying to do is actually multiplying them in a sense of element-wise multiplication. Okay? So we're multiplying the two vectors not as two matrices, but you're multiplying the elements at the same location, right? So this is what we did for signals, and we can again copy them. And I'm going to paste them to the MATLAB command. I'll save it as example number 6. Click on save. Now remember, there's this glitch about the Heaviside function, so I have to apply this double, convert this symbolic calculation to double. Okay. And if I click run, this is what I have. So the clipper is applied in such that for the sinusoidal signal, everything in front of it and after it has been completely eliminated, you only left with this particular section from 2 to 6. Okay, from 2 to 6. Similarly, we can do combination of two signals. This is what example 7 is done. And you can do the copy paste. And remember, for the clipper, make sure you have it implemented with the double conversion. So let's do that again. This will be example 7. So I can copy this and I'll save this. That's example 7. Now this is the example I actually took from the textbook. So the story is in explaining example 1.4 of the book. Okay, so we have the time axis from -10 to 10. We have a constant 2. I took this guy only from -1.5 to 0. So I applied this window clipper to it. And then for the second one is going to be an exponential signal, second component. I applied also clipper to it, and then have the second clipped. And then I add the two combined signal together. I plot the eventual signal afterwards. And finally, this is a new command called axis. It defines after the plot is constructed, what is the limits on the x-axis will be -5 to 5, and what's the limit you want on the y-axis, in this case, -3.2 to 2.2. And remember this glitch about the heavy side, so I have to have double and double here, and this is another place, double and double. So I save these changes, place the figure on this side so I can see it's being modified. So I click on run, and this is what happens. This is the resulting signal, and you can again, as I mentioned, compare the shape of the signal with the one in the textbook. Okay? Example 1.4, and you see what we're trying to accomplish here. So this is the one. And we talk about reversing a signal, right? We talk about time shift. Okay, we talk about scaling. All of them can be done in MATLAB. Okay, I gave a few examples in the following discussions. Okay, for instance, we have a sinusoidal signal, and also it's a decaying sinusoidal signal. This will be the blue curve you're looking at here. Now, if I want to reverse it, meaning I'm flipping it left and right with respect to the origin time equal to 0. So the figure shows this perfect symmetric curve after the flipping. And what I did, if I look at here, is, well, I have my time axis, and I only need to replace t with -t, replace t with -t, exactly as what we did with the formula. And as a result, I plot the two together. You see the result. And you can give it a try on your own computer. To save time, I'll just skip the implementation on my MATLAB. Example number 9, similarly, but we'll be shifting a signal, so we'll be moving it left and right. What I'm doing here is to apply it by shifting the signal to the right by 2 time units. Okay, to the right by 2 time units. Okay. Now again, when you copy this part of the call to MATLAB, remember to add a double in front of this heavy side function because we have to do the conversion. And as a result, this is what you have. Okay. We're moving the signal, this blue curve, to the right by 2 time units, so from 0 to 2, this bar from 3 to 5. Finally will be the time scaling. We're doing fast forward and slow motion. This is the example again. Feel free to copy and paste. Now again, you have heavy side involved here, here and also in this line. Remember to add double conversion as we discussed in the previous examples. Now again, if you look at how this is done, this is the original signal. Okay. This is a decaying sinusoidal signal with a switch or a window function turned on at time 0, turned off at time 3. So this blue curve again is the original one. If you want to play fast forward, replace t with 2t, replace t with 2t, replace t with 2t. If you want to slow down, replace t with 0.5 times t, so half of the speed. Replace t here with 0.5 times t. Replace t in the heavy side function with 0.5 t, t minus 3 to 0.5 minus 3. So this is what we have eventually. We have the original, the blue curve. The red one will be the fast forward, and the orange yellow one is the slow motion. Now another thing that MATLAB can do is to do symbolic calculation. Meaning it can calculate some of the operation like differentiation, like integration. What it does is define a symbol using the sims. So sims t meaning t is defined as a symbol. And you can define a function, so y exponential of 2t. Now y is just, in this case, it's not, doesn't contain any number in an array, just a symbolic notation. But it's exponential of 2t. And you can take the derivative, and you can take the integration. So if you want to run this, for instance, we'll do the demonstration. We can copy, and if you are tired using the script, you can just come back to the command window, activate it, and paste it here. Plus, press enter. And if you want to know, okay, I defined y earlier, but I forgot what it is. You type y. Oh, it tells you y is exponential 2t, exponential e to the power 2t. And I calculate y sub d. By the way, I calculated yd should be the derivative of y with respect to t, and in this case should be 2 times e exponential of 2t. Let's see. Well, exactly as we expected. And y sub I, as I put in here, should be the indefinite integral of y. This y and t, I and t represent integral. Now if you took it, you should see half of exponential 2t. This is from your single variable calculus class, you know this. But now MATLAB can replace all of this effort to save some time. Okay. Now in the second lab, we'll use more complicated functions related to symbolic calculation. For the first one, we'll just stay with this simple scenarios. And this is what you just saw. Okay. And you can do, as you can see, you can do definite integral when you specify the range. You can define your Heaviside function. In this case, Heaviside function is directly a symbolic signal. Right? You can do all these kind of things. And lastly, let's see, lastly we have the delta function that we have been talking about. So let's run this guy quickly. So I copy them and coming back to my MATLAB. And I'm seeing too much. Let me first clear my command window and let me clear the memory, the workspace. So everything's done. I Control V, so I paste the code I just copied from the document. Press enter. Well, MATLAB does all the calculation. So what I do have is, if you look at this D, D is the product of two signals. One is the exponential of t, exponential signal. The second is a Dirac function. Dirac is our unit impulse signal, but it's not delta of t, but delta of t minus 2, meaning this spike is observed, or the spike appears at time t equal to 2, not the 0, not at the origin. Okay. Because of the sampling property, if we're taking the integral of this function d, you have done this in your first homework assignment, okay, depending on if the spike is included in your integral, if you're taking the integral of d from negative infinity to 3, meaning the spike is not involved, then the result R1, the integral should be 0. Now if your integral contains that spike, which is at 2, and now the integral from negative infinity to 3, well 3 is in, 2 is in there. When you do the calculation, the integral should be equal to this guy evaluated at where the spike is observed. The spike is over t equal to 2, so the result of the second integral, R2, is exponential to the power 2 when t equal to 2. Okay. Try to practice this, change the numbers, but try to get a sense of how these commands are being used. And again, myself, the TAs are happy to help you if you run into any issue. So what do we need to do? What I'm asking you to do is the following, after all that example. You will have 3 assignments. All 3 of them are from your first homework assignment, believe it or not. But now, instead of doing that by hand, you'll be doing everything by using MATLAB. Okay. So, assignment number 1 is to construct and plot the signals, okay, using what you have learned above, and maybe you need to use some clipping or time shift, okay, through the Heaviside function and so on. Assignment number 2, you're going to apply some of the time shifting, time transformation, time scaling, reversal to the signals you're dealing with in problem 1.3-3. This is the one again you have look at in your homework. Now assignment number 3 is to use the symbolic tool to solve the integral related to the Dirac or to the delta function. You did this by hand. Now you're going to play with it using MATLAB. In a way to define a symbolic signal will be like this. This can refer to this example. The only thing you need to change is how to now define your D. Okay. And also how do you define the interval? Are you doing negative infinity to plus infinity, or are you doing the integral from a specific range? Okay. Now, as far as submission is concerned, I will need you to turn in the following and organize all these items into a single PDF file. Okay. I will need your MATLAB code for each of the assignment, every one of them. And I will need the figures generated by MATLAB, especially for assignment number 1, assignment number 2. You'll need to construct the signal and plot them. Okay, so I'll need to see the figures. And I want the figures to have the font size equal to 18, so that will be larger, will be legible to us. Okay. In the previous example, you should already know how this can be done. For assignment number 3, I want you to show the screenshots that you run the command to obtain the results. So it'll be this one. So I want to see sort of a screenshot of this nature where I can see our command being run and I can see the results that are shown. Okay. And keep in mind, I want you to combine everything into one PDF file. Don't give us 3, 4 separate files. It will be very difficult for the TA and the grader to create them. And they should be uploaded to the corresponding link on Husky City. So the lab assignment is posted on Husky City as a assignment. You should be able to turn in and upload your work on Husky City online. Okay. So again, if you run into any issue, try to find your TA, myself. We're all happy to help you, and feel free to use the help file online. They're everywhere. You can easily access them. And the due date for this assignment is March 9th. So you have plenty of time to work on it. Okay. Now, what you will expect is, although this one is due in a month, give you a sufficient amount of time, I will assign the second lab next week, and you will also have a month to finish that. Okay. So don't postpone everything to the last minute. You want to start a little bit earlier. As soon as you finish, you can turn it in. Okay. Okay. So that's all I want to talk about for the lab. If you have any questions, feel free to find me, and we'll be happy to help you. So that's all for all the videos, and hope to see you all next Tuesday in class.